Okay, good morning, everyone. Welcome to class. So on the agenda for today is section 13.2, derivatives and integrals of vector functions. Before we get there, I just want to remind you of a few things. So number one, I had to change my office hours for today, so I'll be available later on today. There was a message posted on Canvas about that. So I'm not going to be available from 10 to 11:30. I think I said 5 to 6:30 I'll be available. So the other thing was the participation quiz from Wednesday. There were some issues getting it to show up properly on Canvas, which are fixed now, so that quiz is up. There's a participation quiz for today that's up. So I made the due dates for these Saturday, 11:59 p.m. They shouldn't take very long. So just make sure that you take a look there, get those problems done. And just another reminder about our discussion quiz on Tuesday. So make sure you don't forget to go to your discussion on Tuesday. You don't want to miss that.
For discussion, is it like 50 minutes long quiz?
Yeah, it will take the discussion section. So it might be a little bit shorter than 50 minutes, just so that the TA has time to check everyone in and deal with the mechanics of proctoring you via Zoom, okay? So it will be proctored by Zoom during your discussion quiz. So you're gonna have to make sure you go to discussion, be willing to put your camera on so your TA can observe what you're doing, okay? Any more questions? All right, so without further ado then, I'm gonna start 13.2 as usual. Please don't be shy about asking questions. So I'll try to keep an eye on the chat, but if I miss something in the chat, don't be shy about just unmuting yourself and asking. So let's do this. Just to share. Okay. So 13.2 in your book is about derivatives and integrals of vector functions. All right, so let me get my thing set up here. Distance. Okay. Okay, so let me, did I think, let's see here. Sorry, that didn't work the way I wanted it to. Let's go back here. Participants. Okay. All right. So the main idea is that derivatives and integrals are defined in terms of limits. Oops. So for a scalar function, you might remember df dx, say, is f, oops, is the limit as h goes to 0 of x plus h minus f of x over h. And there's a picture that goes along with this. There's a geometrical interpretation. So there's your x, call that y. Here's a curve, y equals f of x. You could draw a tangent line to your curve. And the idea of the derivative is that you look at a secant line, which just means a line through 2 points on your curve. Let's say this is at x and at x plus h. And this difference quotient we have here is the difference in the y values over the difference in the x values for these 2 points. So that's really giving you the slope of that secant line. And as these base points come together, as h goes to 0, this point moves down, this point here moves down the curve to this guy. So as h gets smaller, these 2 points come together and your secant line becomes your tangent line. So geometrically, you can think of the derivative as representing the slope of the tangent line to your curve. At whatever argument you're talking about, right, that at that position at the curve, the value of the derivative of the function gives you the slope of the tangent line to the curve. So if we try to extend this idea, okay, is there a question? Did someone have a question? Okay, please ask if you've got a question. Otherwise, try to keep your mic turned off. So if we want to look at the derivative of a vector function, say r of t, and we just basically copy what we did for scalar functions. We get a very similar looking equation, except that now this is a difference of vectors on the top of our fraction. That difference of vectors you can work out component by component. So let's say, for simplicity, r of t is a 2-component vector, and let's say the components are f and g. Then this guy is going to be equal to the limit as h goes to 0 of f of t plus h, g of t plus h, minus f of t, g of t, all over H. And if you remember that limits operate component by component when you apply them to vectors, if you look at the difference of these vectors and you do your vector arithmetic, use what you know about limits, you see that you can manipulate to get to here. But what do you have here? Well, in the first component, that by definition is the derivative of the function f evaluated at t. And what about the second component? That's the derivative of the function g evaluated at t. So what happens when you differentiate a vector function? You just differentiate the component functions. Okay, so differentiation acts component by component. That's the algebraic idea. All right, so does everyone have what they need off of this page? Are we ready to move on? We're good? Okay. So algebraically, we're going to differentiate component by component. Now, there was also a geometric interpretation of the derivative as the slope of a tangent line in the scalar case. What's the corresponding geometric idea, if any, for the vector functions? Well, again, it's probably easiest to think about this by drawing a picture. So let's say this is x and y. And again, I'm just operating in 2D to make drawing the picture as easy as possible. So a vector function you can think of, right, as an arrow like this. It's got a direction and a length. And let's say that this is my vector function r of t. And that here is my arrow for the vector function r evaluated at argument t plus h. If you subtract those, of course, you're going to get a vector. And the vector that goes between these guys is r of t plus h minus r of t. So notice this is the tail. I've got my head here. If I add r of t plus h minus r of t, add it to r of t, I get to r of t plus h. So we need to remember how vector addition subtraction works. But based on this picture, notice that r of t plus h minus r of t tracks the graph of the function fairly closely, right? This curve I drew is the graph of r of t. Remember that a vector function you can identify with a curve. And that curve is just the set of points traced out by the head of your vector r of t when the tail of the vector is always at the origin. So when h is small, these two arrows are pointing at, are getting you to 2 points on this curve, which are close together. So the arrow connecting them is going to sort of line up with that curve very closely. And in fact, you can imagine that as h gets smaller and smaller, this vector is getting closer and closer to being parallel to the curve. Right? A little section of the curve looks more and more like a straight line, and this vector is going to be better and better lined up with that straight line as h goes to 0. So we say that this becomes tangent to the curve. Okay. Now, at h equals 0, we just have r of t minus r of t is equal to the 0 vector, which is not very useful, right? We want something to survive as h goes to 0. So we can, in fact, look at the ratio of this vector difference divided by h, and that's going to give us exactly our derivative, right? Okay, so sorry. Does everyone have what they need off of this page before we go on? All right, so can I get some feedback, please? Do you need more time on this page, yes or no?
No.
Okay, good. All right, so if we look at the derivative, because of the geometry, it's telling us something about the graph of the vector function, just like with scalar functions. And in fact, what it's telling us right, so this is the graph of r of t. As t varies, we're tracing out this curve in some direction. And r prime of t is going to give you a vector which is tangent to the curve. And so the important thing is the direction if you're interested in the geometry. We'll see later that we can build the so-called unit tangent vector, capital T of t is equal to r prime of t divided by the length of r prime of t. So that's a unit vector tangent to the graph of the function. That extracts only the geometrical information, right? Unit vector has to have length 1. If we work with the derivative itself here, the length of that vector does have some information. Effectively, it's telling you how quickly the curve is being traced out at the point. Okay, and that makes sense if you think of r representing position in physics. The vector r prime of t is your velocity. And the length of the velocity vector is the speed. It's how fast the particle is moving. If R represents position of the particle. Okay, any questions there? Are we ready to go on? We're good? Okay. So there's some rules for differentiation that you should keep in mind. Most of these are differentiation rules. Most of these should be familiar from derivatives of scalar functions. But there are some new wrinkles to keep in mind. So if you take the derivative of the sum of two vector functions, you get the sum of the derivatives of the functions, right? For this really to hold, both sides have to be well defined. All right, so that's the thing you have to be careful about. If you take the derivative of a scalar multiple of a vector, you can always move that scalar multiple out in front. So you can pass constant multipliers through the derivative. Okay, that's the same as for scalar functions. And just notation, sometimes we'll use this Leibniz notation, du by dt. Sometimes it's convenient to use the prime notation for derivatives. Depends on what you're doing and sometimes just your personal taste. But both types of notation are out there. You should be familiar with them. If you need to differentiate a scalar function times a vector function, effectively what you need is the product rule. If you think about how scalar multiplication works, right? Multiplying by a scalar means multiply every component of the vector by that scalar. Differentiate the vector means differentiate component by component. So you're going to have the product rule in each component. And then you can back that out to write it this way. So differentiate one of the factors, in this case, the scalar factor, plus leave the scalar factor alone, but differentiate the vector factor. Okay, so product rule works exactly as you might expect it to. But now there's a few versions of the product rule because we have a few products. Few types of products. So this first guy here is the product of a scalar function with a vector function. You could also have the dot product of two vectors. And again, sort of the structure looks the same, but notice that you have to make sure that you don't forget you're dealing with a dot product, right? Dot product is a scalar, so your answer should be a scalar. Each of these pieces that comes out is a dot product itself, so it's going to give you a scalar. And we also have a cross product of vectors. And again, the product rule works the way you might expect it to. You're going to differentiate one of the factors at a time. Right, so, but with the cross products, you have to remember that the order of the multiplication matters. So I have u times v prime plus u prime crossed with v. Right, I left the u's on the left, the v's on the right. Okay, and then finally, Does everyone have what they need off of this page? The last equation. Kaveri, can you see this last equation, or what was the question exactly?
It was on the previous page.
Sorry?
It was on the previous page.
Oh, sorry. I'll write it over here. So the unit tangent vector by definition is your derivative of the vector function r divided by the length of the vector function r. Right, so that is guaranteed to have length 1. It's a unit vector, right? As long as you're not dividing by 0 there. That's well defined, and it's going to be a unit vector. And what this extracts is just the direction information. So it gives you the tangent to the curve. Okay?
Yeah, thank you.
All right. So we have our differentiation rules. The last one, I don't have space here, so I have to go on, is the chain rule. If I want to differentiate a vector function where instead of t, I pass some function of t as the argument, we're going to get sort of what you expect from the chain rule, but you have to remember that the quantity you're dealing with is a vector quantity. So where does this formula come from? Let's just think about taking the derivative of a vector function, and let's say we have x of f of t, y of f of t. Well, differentiation works term by term. So in my first component, I have x of f of t. When I differentiate with respect to t, I have to use the chain rule. And same thing for the second component. And notice in each of these, I have this factor of f prime of t from the chain rule. So that thing I can move out in front. All right, so because differentiation is defined term by term, basically all the differentiation rules you know can be applied. You just have to make sure that you apply them correctly. Things look very, very familiar. Okay, any questions on the chain rule here? Are we good? Oh, good. Okay, so integration, again, works component by component. And I'm not going to go through the definition of integration like I did with differentiation. Let me just write. Come on, work. So this is a so-called definite integral. And how do we interpret this? Well, we're going to apply this integration to each of the components. So we're going to integrate from a to b f of t dt, and we're going to integrate from a to b g of t dt. Okay, so again, you know a lot about integrating scalar functions from Calc 1 and Calc 2, so you can directly use that knowledge when you have to integrate a vector function because you do everything component by component. Okay, I wrote this out for a 2-component vector. Same thing works for 3-component vectors. If you want, you could write this in terms of the unit coordinate vectors as well. Doesn't really matter, right? These are just 2 different notations for vectors. That's the definite integral. Any questions there? Are we good? Okay, so what about the indefinite integral?
Sorry, could you come back to the previous slide? I didn't have the screenshot.
Okay, do you just need time to copy?
Yeah, I'm good now. Thank you.
You're good, okay. Very good. Definite. So remember, something like this is an indefinite integral. So in the scalar case, what does this mean? It means find the most general antiderivative. Of the function that appears under the integral sign. And that means, so for instance, something like this, if I had t dt, you have to remember the constant of integration. So the fundamental theorem of calculus says antiderivative and derivative operations are in some sense inverses. Doesn't work quite as cleanly as that because of the constant of integration you have to remember when you're finding the most general antiderivative, but that's a good approximation. And because we're going to operate component by component for the vectors, right? Essentially, we have a scalar function in each component of our vector. So we're going to get a scalar constant of integration for each component of our vector. So if I have something like this, t e to the t, and I want the indefinite integral or the most general antiderivative of this, I'm doing that operation of finding the antiderivative in each component. And these constants of integration that come in for the different components are independent of each other, so you can't really give them the same name. Usually I try to do something like just use the same letter and give them different indices. Now, you don't have to write everything out the way I did here. You could pull off the constants and just make a constant vector that you add on the end there. And that's perfectly fine to do that. But the thing you have to be careful of is that you have to make sure that it's clear when you're dealing with a scalar versus dealing with a vector. So if I just wrote something like this, I might get a problem wrong because it's not clear that this constant c is a vector constant. You want to put an arrow on top or draw a bar underneath. You want to indicate that what you're dealing with is a vector constant of integration here. Okay, is that clear, everyone? Are there any questions on this page? All right, so everything you know about integrals and derivatives from Calc 1 and Calc 2 in principle, you should be able to draw on in Math 243. So certainly powers, you should be able to integrate and differentiate exponential functions, trig functions, but also things like inverse trig functions, integration techniques like integration by parts, integration by substitution, everyone's favorite partial fractions, right? These are all fair game in principle. We will try not to get too elaborate with the integrations required, but you should review integration and differentiation if you're feeling a little bit shaky there. So I'm going to just jump ahead a little bit. So 13.3 has to do with arc length and curvature. And there's a formula which I think you see in 242. So if you've got a parameterized curve, let's say with, let me write it like this, x equals f of t, y equals g of t, and t between a and b, there's a formula for the length of the curve, which I know is covered in Math 242. Okay, so hopefully this is familiar. Now, if you interpret this in terms of vectors, right, essentially you can use this formula. Again, reuse it. Right, so the formula for arc length involves the derivatives of what we recognize are the components, component equations. And we want the square root of the sum of the squares of those, but that's just the length of the derivative vector. Why is this not working? Okay. Okay, so we could reinterpret that arc length formula in terms of vector functions. Okay, so that's one of the topics in 13.3. That's one of the places where integration differentiation interacts with vector functions. Okay, so I just wanted to point that out. All right, so any questions on that? Do you remember seeing this, guys? Okay. All right, so let's try a few problems. So here's number 3 from 13.2. We've got the vector r of t is 2 t squared plus 1. And the question asks you to sketch the curve to find r prime of t and sketch the position vector and tangent vector for the given value of t. So notice that x is equal to t minus 2. So t is really the same as x plus 2. Y is equal to t squared plus 1. Now I know how to write t in terms of x. So y is equal to x plus 2 squared plus 1. So one of the strategies that you might remember from 242 for sketching curves is to eliminate the parameter. Sometimes that helps you recognize the curve as a standard curve that you understand. So what type of curve are we talking about here? Does anyone recognize that? It's a parabola. Very good. Many people are getting that. So that's a parabola. Okay, so so we can sketch that curve. Y equals x squared is sort of the simplest parabola. So if we know that, we can sort of by some transformations figure out what y equals x plus 2 quantity squared plus 1 is going to be. So in fact, that plus 1 just shifts the parabola up by 1 unit. So this is y equals 1. And the shifts from x to x plus 2 is a shift either when you add or subtract something from x, a shift like that shifts your graph left or right. Okay, so I know that the vertex of my parabola is going to be at x equals minus 2. And my parabola is going to look like this. And I'm not going to, actually, I should be careful. I don't want to draw the arrows here on the parabola. I'm actually going to think about how is this curve traced out if this is my parameterization. So x is t minus 2. As t increases, x increases. So as t increases, I'd be getting points on my parabola. I'll be tracing it out sort of left to right like this. So these arrows show you how the parabola is traced out as t increases. And what were the other parts? We want to find r prime of t. Well, let's just differentiate. The derivative of t minus 2 with respect to t is just going to be 1. The derivative of t squared plus 1 is just going to be 2t. So that was easy, just polynomials. And we want to sketch the position vector and the tangent vector r prime of t at t equals -1. So at t equals -1, the x value is going to be -3. So we're going to be over here, say. Right? So the vector from the origin is going to take us out to that point. The position vector of that point starts at the origin. And what about the tangent vector? What about r prime of t? Well, I've got r prime of t here. Notice that it has a positive x component. If t is -1, the y component is going to be -2. So I have a vector maybe that looks like this. My artistic talent is limited, but that tangent vector locally gives me the tangent to the curve. It's telling me as I'm tracing out the curve at this point exactly what's my heading, in what direction is my pencil moving as I hit that point when I'm tracing out the curve. Okay, so is this clear to everyone? Is this making sense? Is this good? Okay. So we only have a couple of minutes left, so let's do some integration. Okay, so this is problem 35. And written in terms of your coordinate vectors I hat, j hat, k hat, really you can act as if these were just constant multipliers, right? T I can integrate to t squared over 2. It's going to get multiplied by I hat. T cubed is going to integrate up to t to the 4th over 4. It's going to be multiplied by j hat. And notice this is a definite integral, so I'm not worrying about constants of integration. We have 3t to the 5th. That's going to integrate up to t to the 6th over 6. K hat. And I'm going to go from t equals 0 to 1. So upper limit, I plug in t equals 1. I get 1/2 I hat minus 1/4 j hat. 3 over 6 is 1/2. That's 1/2 k hat. And then at the lower limit, everything evaluates to 0. So I've got my answer. And if you like, you can write this in angle bracket notation just as well. Means exactly the same thing. Okay, any questions there? Are we good? Okay, so let's just do one more. If we do an indefinite integral, and let me just make up one that's not too hard. We're going to integrate each component term by term. So an antiderivative for e to the t is e to the t, and then I can add a constant of integration. The derivative of the sine is the cosine, so antiderivative for cosine is the sine. Have to add a constant. Oh, yeah, so question came in about what we were doing here. I wrote zero vector rather than just the number zero because remember, these are vector quantities. I can't add a vector and a scalar. All right, so alternatively, I could have written this out as 0 I hat plus 0 j hat plus 0 k hat. Okay. And then finally, the t integrates up to t squared over 2, and I have to remember my constant of integration because it's an indefinite integral. All right, that's, I think, where we have to stop for today. Thank you for your attention. If there's any questions, please ask. I can hang around for a little while to answer questions, but not forever.
Thank
Right.
you.
Okay, have a
Thank
good
you.
Thank you.
Thank you.
Do you have a question, Vaughn? Oh, okay. Minghang, do you have a question? Okay, I have to leave soon. Please ask if you've got a question.